Hello everyone. Thank you for the introduction. My name is Junkai Zhao, and I'm a robotic algorithm engineer at the Beijing Academy of Artificial Intelligence. My topic is about learning from human demonstration, a new paradigm for scalable robot data acquisition. So here is agenda of my presentation. First of all, I will give a short overview in the area of robot data collection, and second is humanoid data collection pipeline, and lastly I will give a few demos, and the final is question. So in the area of embodied AI, we have witnessed the efficiency of various kinds of models, large models, small design model for some specific tasks. In robotics learning, learning from demonstration has been shown as an effective method. The question is, the first important thing is robot data. So you need precise and real-world data for the training. The question is, how can we efficiently get this large-scale robot data? And there has been several works about robot data acquisition. I will give a short overview of these types of data collection pipeline. The first type is laser follower arms, and it's proposed in the work Aloha. And as here, as you can see, the human operator operates two laser arms, which is close to the operator, and the two follower arms keep the same motion with the laser arm. So during data collection, the human operator operates these two laser arms, and then the follower arms will record this robot action. And it has advantages. For example, it can keep precise joint recording, because this joint recording can be directly recorded from the motor. But at the same time, it has also disadvantages. First, this type of data collection mainly focuses on parallel jaw grippers. And in ordinary works, parallel jaw works is restricted and can be only deployed to small objects optimization. And lastly, this type of operation system is restricted to specific robot platforms. As you can see from the picture, the data is only related to this type of hardware. And when you get this type of data, you can only train the policies that can be deployed to this type of hardware. So this is the first one, and based on that, there has also been the second data collection system named Vision-Based VR. As its name suggests, human operator wears VR, and in this picture, for example, Vision Pro, and the Vision Pro can detect human wrist pose and finger poses, and retarget to the humanoid robots. And it has advantages. For example, it is not only restricted to parallel grippers. It can be deployed by manual arms with dex hands, and it's portable because the operator don't need any operator some hardware, and the human operator can only wear we are a Vision Pro, and the the disadvantage we have also tested this type of collection pipeline, and one thing that that we think is most disadvantageous is that it's tired. It's easy tiring because a human operator cannot see the physical world. It can only see the camera stream from the humanoid. So after long time of wearing this glass, the human operator can be easily tired. And also because the wrist pose and the finger pose are detected by the vision. So under some occlusion, there would be inaccuracy. So the second system, and I think this second system can have both the advantage of the last two systems. It's a vision exoskeleton teleoperation system. As its name suggests, the human operator wears a skeleton, and the hand is detected by the camera in the bottom of the human hand, and you can see.
I'm sorry.
No problem. And you can see from the video, and there's two small camera in the bottom, and the camera is for the human hand gesture detection, and it can detect the human hands, for example, picking and releasing. And the skeleton records the arm joints, and the arm joints can be directly retargeted to the real-world robot, and it can record the arm joints, and it can be deployed onto DEX hands, and it's also portable. You can the human operator can place can wear the exoskeleton or put the exoskeleton on the table, so it's portable. But there's no head tracking. So if you need some work that need to turn to rotate your waist, and not only focus on the table, so this type of teleoperation system cannot do that. Okay, and because the human hand joints recording is also vision based, so in some situations there could also be inaccuracy for the hand joints. And the last one is you need to retarget the joints of these exoskeletons to the real world robot. So if you change to another robot, you must do some additional configuration. So it cannot be easily to transfer to another robot platforms. So here is the question: how can we set up an efficient, precise, comfortable, and cross-embodiment robot teleoperation system? So here is our plan, and it's portable because the human operator can only wear a glove, and there are also two trackers attached to the glove, and it's named the VV tracker. The VV tracker is to detect the wrist pose motion tracking, and for the pose tracking, there's no external devices, so you can theoretically you can take this tracker to anywhere. And the glove is named Manus Meta glove, and because this Meta glove records the precise hand joints, so even in some even in some occlusion, and the glove can also record precise finger motion. Yes, so no external tracking devices are needed. So it's portable and it's precise and it's comfortable because during teleoperation, the human operator can see the physical world. So it can see the robot and the item. So it's portable and it's across platform because we only record the end effector, namely the two hands pose. So if you have the end effector pose, you can transfer theoretically any robot hardware to control it.
Can I ask you, please? We've got head.
Okay. Head, because we have 3 VV tracker, and 2 VV tracker is attached to the hand, and the head one is attached to the human operator. It's to the head of the human operator. So in this picture, I don't show the whole body of the human operator. So I just put on.
What is that capturing? Oh, sorry.
I will.
After.
Yes, I will describe it later. So it's our pipeline, and for the human hand joints recording, we have SDK, and we get the human hands from the SDK, and after that we do a fingertip retargeting, which I will take it later. And after fingertip retargeting, we get the real hand, DEX hand joints, and use the joint control. We control the DEX hand, and additionally the VV tracker. From the VV tracker we get the human wrist pose, and we use universal kinematics to get the end effector in the robot coordinate system. And for test, we use Unitree G1 with 2 inspired DEX hands, and we record robot wrist pose and DEX hand joints and head camera stream to collect robot data and train the policy. And for the fingertip retargeting, why we do fingertip retargeting is that the DEX hand has a different size of human hand. If we directly use the joints of human hand to control the DEX hand, there will be physically shape difference between human hands and robotic hands. So we must ensure that the fingertip of both human hands and robotic hands is in the same position. So when human try to grasp something, the robot DEX hand can also form the same shape with the human hand. So the principle is it's a kind of optimization problem, and here is a question for how we do fingertip targeting, and VIT is the key point vector from the detected finger key points and QT is the DEX hand joint positions, which we get directly from the SDK, and F is DEX hand forward kinematics, which means when we get the human DEX hand joints, I can calculate directly the key point of DEX hand position in the hand coordinate system. So after this optimization, we get the optimized QT. So I can get put the QT for hand joint control. So next is rest pose retargeting. So here you can see the wave tracker in the head. Because the wave tracker, we have 3 poles: the left hand, right hand, and the head pose, and they are all expressed in the world coordinate system. And the right one is the unitary G1 coordinate system. The origin of this robot is in the waist, and you need to retarget the human hand to the next hand, and so we retarget it. Retarget so that when human hand move forward, and the unitary G1 next hand can move forward. And also, the in-hand tracker ensures a smooth and precise wrist pose tracking, because this kind of wave tracker is vision-based, and even so it can record any movement of humans. There is also no need to external devices to in front of the human operator. So if you can use this device to teleoperate your robot in everywhere. So here I will show you our teleoperation process. And the unitary G1 put a pitch on the bracket and hand it to the human. So there is no external devices, only the glove and the tracker. And so the recorded fingertip and rest position can be used for the policy training, and the tracker and the human hand joints can be recorded at a high frequency. And after data collection, and we train a model to replay our collection, and you can see this demo. It's in real time. And using this data collection pipeline, we can train some special, small special models for integration to VLM to solve long horizon tasks. And the policy route frequency is in 30 Hertz. So that's all, and welcome to our booth in the first floor. If you are interested, please, you can have a talk with me.
Thank you.